Okay, so great to be here. I actually did part of my PhD here some time ago, so it's always nice to be back. I have my background working at VTT in Finland, a big research institute like RISA used to be. And now I just in January moved to Thailand, so now I work for my own company Recognis, but still do subcontracting to VTT for this international collaboration IEA Wind, from where I'm presenting today. And I thought that the subject grid support from wind power plants would be sort of general enough and still related to the main presentation we will hear today at 1 o'clock. So I will talk a little bit about the power system point of view for grid support and the examples of the experience we have so far of wind power plants actually providing these services using the capabilities that they have. And then I will use some of the time actually to talk about the needs for future studies, which is really interesting and exciting for really high shares of wind and solar, sort of up to 100%, so that wind power plants would be the backbone of the power system. So this IEA Wind Task 25 is an international collaboration. We have 18 countries participating. Denmark is one of the active participants, both Nikos from DTU and then also the TSO Energinet has been very active there. And so we share all the experience and study results and produce these reports, these summary reports every 3 years summarizing the recent findings, and then we do guidelines as recommended practice reports for the IEA Wind, and the last one we did with solar PV, and then we do fact sheets, and we have some time series that could be useful, and a literature list, and all is available in our webpage. So they're going for the grid support. So this is an example made in France, where they did a study for the whole big European system having 60% renewables and how it would look like. So we have already seen in Denmark that when a small country like Denmark has 40% on average coming from wind, so Denmark is the pioneer there, so it's quite common that more than 100% of the electricity consumption comes from wind. But even in the big European system, as a synchronous system, we will start having these situations where the net demand goes to negative. So the demand minus wind and solar will actually sometimes be negative. There's more wind and solar than the demand. So this is for a power system. I mean, Denmark can deal with its neighbors a lot of these issues. So wind is still not more than the demand in the larger area. But we will start seeing these situations, these hours, when we have 60% renewables in Europe. And then the question is, how do we do the balancing, and how do we do the frequency support? And we do have at the moment operating reserves with these. Of course, the variability and uncertainty of loads has been there always, and now just adding wind. And basically we have this is like a history of the early days of wind integration. Then you start looking, okay, what's the impact of wind, and you can't just put it on top of what's the possible event of your largest power plant tripping off, and what's the possible worst thing that can happen on your load, and the worst thing that can happen on the wind, because you would just over design your system and use a lot of money. So somehow you need to start doing these probabilistic analysis and putting this variability together. And this is like some of the things that the grid integration studies have been about. And then what we have tried to look from the experience, well, this is still from the studies. Then you can do these studies, and these have been done a lot, and then you get the results are all over the place. You have increasing wind share on the x-axis, and then you basically have an increasing sort of need for these reserves for balancing. You do see that when you just look at the hourly variability of wind, then the results are pretty similar. But other than that, if you look at different time scales, then you can have very demanding impacts of wind. But then when we start looking at the experience, what actually happens is, for example, in Germany, then you see the curve that is going upward is the wind and solar, but what is happening in the bar chart over the years of how much they actually need these operating reserves, it's actually going down, which is of course totally different what we see in the studies, and this is because other things are happening in the power system, and Germany has been doing more and more sharing of balancing between their different system operators. And actually, even with ongoing wind, when you start operating your system more wisely, then you need less and less balancing resources when you just share them. And this is, of course, the Danish experience as well, but the Danes never had to sort of first start using a lot of them and then going down, but the Danes from the start have been using their neighbors for helping in balancing. And then, of course, it will be easier when you also start using wind power as a means of balancing. So you have this frequency support for different time scales, and what we have seen so far is that the downregulation is pretty straightforward when it's needed. You can ask the wind power plants to do downregulation, and you can bid downregulation to a market, and when it's needed, it will be contracted from the market, and then it's pretty easy. And then we also see that the faster ones operating in the second time scale is also already used in some countries. Voltage support, we do have demonstrations about it. It's technically okay, but the implementation is not that straightforward. And for example, maybe surprising, but here in Denmark, it's not really used. And one reason is that when you build these DC links, these interconnectors, they actually can provide a lot of voltage support at the same time. So it's not so much needed in a system like Denmark. And then what is also emerging is the supporting of stability and studies on even black start and providing sort of more and more system support from wind. Then going for the experiences that we have. So Spain has opened its market for smaller power plants generally, and mostly it has been wind, so it's more than 90% then that they saw were coming were wind power plants. So it's now 15 gigawatts of their about 23 gigawatts total installed in Spain. And they have been making these compliance tests, where you can see an example here from Red Electrica, their system operator, that they just have to prove that they can follow set points for providing the secondary, the more automatic reserves. And mostly they have been providing so more down reserve than up reserve, and and more of this sort of minute time scale reserve. But it was 5% of the system operator needs in 2017 already, when this was first starting, and it is increasing. So we do see that from the system point of view, it's utilized. So there is already a need for it a little bit, and then it's good for the wind power plants also that they are in the market and they will get some payments from the market. Another example is then about the faster, the automatically operating reserves, and this is from the US already for some years back. the Colorado system was had so much wind during night times when there was low demand that they sometimes had to curtail the wind power plants. And then when they were anyway curtailed, like in this case, you could see here, they started curtailing, and then they were measuring the area control error. That's what they measure in the US in the balancing areas. And then they started this automatic generation control from the wind power plants. And then the wind power started producing so that they would give the support to the grid, and then the area control error was more stable after that. And this is just an example showing that this works really nicely. This was just during these situations where wind was curtailed anyway, and then able to provide this support. And another one is a smaller system. The Quebec is a different synchronous system, so it's about the size of the Nordic synchronous system, so not very large, sort of mid-sized synchronous system. And they have required that the wind power plants must provide inertial support. And then they actually had an event where this very fast, almost like inertia type of response was required when a generator was tripping off. And then they measured, and they could see from their different wind power plants that they had actually provided some of the support. And this was then all reported as a conference paper that this works. This is something that they don't pay for, but this is also very seldom happening, that you would have these kinds of tripping off events, and then the frequency would start going down quickly, and then you would have to have this upward responding, very fast responding in some seconds. And then what is the problem when the wind power plants are not operated in curtailed mode? Then they have to give this or take this kinetic energy back, and that's why you have then this bump. So it helps in the beginning, and then other power plants will take it from there. Like hydropower plants are a bit slow, work in a bit slower mode actually than wind power plants. So it makes a nice combination, wind and hydro. And then really cool example, I think, is this. Again, we see a trend of downward regulation needs, and this time it's really the fast response regulation needs from Texas system. So at the same time, the wind has been growing, and they use less this very fast response. So what happened is that they put all their wind power plants in this very fast primary response, and also quite low, sort of tight band in the frequency. So the wind power plants, as soon as the frequency is going a bit too much up, the wind power plants immediately go down. And since wind power plants are so fast, they are wow, they are so fast, and they really operate accurately, because often power plants, I mean, you don't often know whether you will actually get what they promise, but the wind power plants are reliable and compliant and extremely fast. So then they already managed to keep the frequency in that band so well that they don't need this regulation, this secondary response, as much as they have been using before. So also I think this is a very nice example how good the wind power plants can be. Okay, then looking a little bit from the wind power plant point of view. So usually we have had most of our payments from the blue energy part, and then a little bit is paid for system services. This is also like reflecting that most of the megawatt hours are sold as energy, and there is a little bit then sold as grid support and frequency support, balancing. And then what we see in future is that perhaps we need to pay for capacity, because even if the system services would be 10 times more than today, then if the energy only market prices go down, let's see how it goes, how we manage to get the revenue sufficiency. But also, of course, wind power plants see this drop in the prices even more, because it's mostly caused by wind power. When there's too much wind power, the prices will drop. So then this also for wind power plants, this market revenue from ancillary services would be very important, and that's why it's very important that wind power plants would be enabled to take part in the markets, like the example of Spain is showing. And then they could gain extra. This is an example just calculating that if you just put a point forecast to your day-ahead market, or if you start bidding strategically or aggregating your wind power plants and move to a shorter gate closure, so you can bid closer and your errors go down, and you start adding other products, so then really you can improve a lot what you earn from the market. But then, of course, there are studies showing that, okay, not all markets are really fit for renewables. You should have shorter lead times. If you demand that a week ahead, you have to know whether you have the ability of going down and up. You can't really bid anything from wind power plants, so you need to be able to bid. Day ahead you can bid a little bit, but not very much. But if you can bid only hour ahead or even some minutes ahead, then you know already so much that it's much easier to use the whole possibility that wind power plants have. Then, of course, for wind power, larger markets makes a difference, because there's a big smoothing impact, and then having the ability to do this cross-border trading is very good. Also, one thing is about smaller products. So there are also markets where you have to have, for example, 10 megawatt bids for going down or up. And then it's also not possible for wind power plants unless they are really big offshore power plants. And then we do have some cases where wind is already used, like demonstrations in Germany, where they actually complain that, okay, now we have all these services, but they are not really used from the market a lot. And what we have seen in one of the EU projects is that actually you only start needing wind power plants when it's 20 or 30% of the total system that you're balancing. And this is why in many places still it's a little bit on the verge of whether the system actually needs the wind power plants. But we also see that once we reach higher shares of wind, it will pay a lot to have these services from wind power plants. It's both that the wind power plants will then go to the market and get more paid, but it's also that once wind power plants can provide these services, then more big conventional power plants can be totally shut down, and the curtailments will be less. And then it's a question that, okay, now we've been talking mainly about these frequency, different time responses for frequency, and we see this sort of inertia and fast primary response coming. It's now in Ireland and Quebec, but studies are made also for other power systems for that. But also we could perhaps have other products of mitigation of the variability, and also going more into damping different oscillations, really going into sort of the microsecond time scale, and protections, and even sort of different stability limits, and how wind power could improve them. This is from the view of Enecon about then how should these be paid. So even the wind power producers can say that some of the services that are only used, for example, when there is a failure, it does make sense that, okay, you in sort of the extreme situations that you would just have it as a grid code, but then probably a lot of the services could be paid for. And this is something that where the markets are still developing, and the market designs need to develop. And also, so one thing is about thinking about what kind of products we need for system support, and then how would they be paid for, or could they be just asked for in the grid codes, in the sort of requirements for grid when they connect. Okay, and then what happens when we go towards 100% fibers? So we are now, let's see if this acronym will live or not, but we've been talking about RES a lot, renewable energy sources, and it's not only wind, but it's wind and solar both that are coming, that are inverter based, and that is something that is also very different, that it's variable, but that it's connected by inverters, and this is sort of the two challenges that we see for the future power systems. So we have different ways of dealing with the future system, that when it becomes more light, so the inertia is less, there is less and less synchronous machines online, and these inverter-based machines, from the grid point of view, they can provide a lot of services through control loops, but they don't physically provide any inertia to the system. But we have different ways of dealing with that. So we can just, like nowadays, what the system operators are doing quite a lot, they are just saying that, okay, we just have to have some of the big generators online. We have to have this must-run generation. Another way is to just say that, okay, we can have synchronous condensers. So these are devices that can provide a little bit inertia, but also other system services, and they are providing zero power. So we can let more and more wind and solar produce and take out the big power plants and just have these synchronous condensers. And this is actually what West Denmark also, or Denmark, West and East both, have installed these synchronous condensers. And then you can have fast frequency response, which is like even faster response than today. It's almost like inertia, like a response. We don't like to, or many people don't like to call it inertia, because inertia somehow involves that it's a physical thing happening, and this is like a control loop response. And then we can go to grid forming, which means that the inverters would be almost like synchronous generators, or they would have this ability to keep the frequency, to follow the frequency in so quick way that they are actually keeping the frequency. And here is one study from France, just looking that when you start seeing increasing renewables, that it looks like you can, in the beginning, sort of this fast response helps a lot, and some place you still need to have these other things happening. and this is not showing the grid forming, because grid forming is a way to go all the way. And then Ireland is an interesting case because it's a really small synchronous system, and they have made the studies that up until 80% it seems to be pretty okay to have these machines, or sort of 80% wind there, and but then their stability studies start showing that it's not really that they really need to think of new ways of going for more than 80%. One really nice example is from Denmark, that was publishing this how they managed to run the system for hours or even a day, so that there are no big power plants operating, so they could really show that just having all the system services from the HVDC links and from the synchronous condensers and then from the smaller power plants, it's enough. They are, of course, one balancing area in a big system, so this is easier for them than for Ireland. They don't have to think about inertia so much because they are part of a big system that still has a lot of inertia. But the other stability things really go, and this is really exciting to see that we have a lot of possibilities. The vision is really that we would be able to operate whole synchronous power systems without any big machines online. So we will just replace this mass, this inertia, with brains and fast controls. And what is still, I mean, this of course needs to still be demonstrated that it goes, and also I mean, theoretically this should be okay. These studies are already made, but even theoretically it's not yet sure how we can do the capability of shifting from synchronous to non-synchronous machines. I mean, there may be some systems where you wouldn't have any synchronous renewables, and then you could just design for wind and solar, but there are still many systems that would have hydropower or geothermal or biomass. So you would somehow need to operate the system in a synchronous mode and not synchronous mode. So we know that with grid forming converters, at least in our studies, it's okay. The wind and solar can support the grid, and then one thing that will come is this local smartness and combining it with the large power system. So this is also a sort of interesting thing happening. So the challenges we still have is that we do have challenges of stability to tackle. For balancing both the flexibility and the adequacy, so how do we have enough generation capacity for all the hours, how much we need storage, and how much the electricity consumption can flex. Could it be even enough for seasonal mismatch if we start producing heat and some industry things from electricity that is not produced by electricity? Can they sometimes be non-operational for 100 hours or even 1,000 hours? So then we could have even some seasonal support from the demand side. And of course this whole market operation, how will this then be done? And these opportunities are happening at the same time, so we start seeing that the load is becoming flexible, the grids are becoming smarter, the inverter controls, we really have just started to look at what can come out of inverters with programming them differently. So there are a lot of possibilities. And one possibility that I would like to stress here is what happens with the load. So we have in our models, we usually use the load is not very flexible. And when we start seeing all the digitalization happening, the home energy management systems, the building energy management systems start coming, energy communities, local markets. So then we have the loads as we have today, but a little bit different. And then what is even more interesting to see is what happens with electrification. So then we start having these totally new types of loads, like for transport, that provide different kind of possibilities for flexibility. So this is like not even same. This is just like totally different things that we will have in the future. So the flexibility options that we have is really a lot. And we have, so both wind and solar and the loads and the storages can all provide these system services. We will have new loads that will be more flexible, and then all these operational practices and tools, when they develop, it is really possible to operate the system in a that is really backbone wind and solar. For the stability, we think we can go either through synchronous condensers or grid forming converters or wind and solar. And this is like something we don't yet know which way we will go, or is there a smart way of combining these. And then for the markets, we know it's going towards real time, more and more smart and fast markets, but really adding these local markets that are now emerging, and making and designing them in the way that the markets really set prices and value for flexibility, so that it's not locked inside one local community, but when it's needed in the system, it's available. This is a challenge, and yeah, this is the idea of a future power system where you would have these autonomous, these cells that could be whatever is the system in the grid. When the big grid is available, we use all the benefits of that, but when it's not, we are just in a medium size or even smaller size cells, and all the time communicating with everyone. So digitalization is the key for this. But yes, a lot of interesting research for sure will still be needed. For stability, for system operation, for adequacy. And I think that when we see a lot of studies made, what is a big change is this sort of, it's not only about energy transition that is happening, it's also this load transition. And I think all our models are really lacking in how we present load in our models. So this will be a big change also in the research we are doing. And then also how we model wind power plants, so that they are really the backbone of the future energy system. I end with an advertisement that we have made these recommended practices for wind integration studies available in the IEA Wind website. And we think that this is also very nice for benchmarking. It has a lot of these bullet point lists of the different simulations that you do for power and energy systems. So I hope it will be used more in the future. And then I thank you. Questions? It's specifically designed, but I have heard it's very much like an Egyptian eye. More complicated, but what is the role? Well, We made a theoretical study looking at 100% renewable energy system. So we really looked at how much the industry and the transport and the heat would need to change. And then we ran a normal year of hourly unit commitment and dispatch, producing all these synthetic gases and electricity for transport and electricity for heating and cooling. And we saw that if so basically then the system is full of electrolyzers with the gas storage. And it's full of, the heating system is full of thermal storages. And the cars have batteries. And in our Northern European system, converting all the cars, all the sort of the private cars to electricity, if it's possible to use them also vehicle to grid so that they are actually battery storages, then that was enough for the short-term storage. That was because the Northern European system would be dominated by wind. If we have a system that is dominated by solar, then I think you probably would put more short-term batteries there. But in the Northern European system, you have quite a lot of hydro storages, and then when you add this thermal and gas and transport vehicle batteries, that was actually enough. So yes, they are storages, but they are not the sort of traditional way we are thinking that we would just build these short-term storages. The short-term storages don't really, I mean, in the solar belt, the system is different because then you have everything. You can have everything from solar and just have your battery doesn't need to be long. So you can manage quite well with solar and a battery. But when you have other options, then you tend to build more wind. So you have solar, but you also have wind and other ways, and then it's a bigger picture. So for sure we will have storages, but whether it will be like we think, because storages are very expensive, and I mean you pay for something that you only lose energy in. You don't get any more energy by building a storage. You just get less energy. So if you have other ways of doing it, like demand response or flexibility in other ways, you would always use other ways. Well, if it's possible to build more interconnectors between countries, then the models will always build them. So it's like the most cost-efficient way, if it's possible. And that for wind power, that will be needed to smooth the low wind days and the high wind days. So it's not, I mean, and I think also that's the result from the NSOE 10-year network development plans, that they always come up with quite a lot more transmission that is proposed to the system. So there is, yeah, I think there is need for that, but we see, for example, in Germany that they haven't been able to build inside Germany from north to south transmission, and then the system becomes different. And whether I mean, if we have this local flexibility really coming up, we don't really see it. It's quite theoretical, but we already see these devices being sold to homes and buildings, and we see the potential from there. So I think that will help the transmission to some extent. So our studies have been looking at with 5-year steps up until 2050 being totally renewable. That is, of course, very theoretical and probably, I mean, will probably not happen, even if we do see these political statements being made in Sweden, Finland, in Denmark, in many countries, that in 2040, 2035, this and this part will be already renewable. But to make it really happen, usually the time frames are 2050 and 2100. So there is time for regulation for that. Yes.
System where you have a lot of energy, relatively free market. Sometimes you have just downward spiraling prices on wind energy zero. How can you measure that?
So basically, the idea is that from electrification there will be so many new loads that our electricity consumption will almost double in Western countries. So these new loads will be there when there is a lot of wind and solar available, and then they will make it so that the prices will not go to zero, and then when there is a scarcity of wind, they will not be operating. So this is really needed. If we have the current system, the current load, it doesn't work. And well, also the electricity markets can work in a way that for example we have 1,000 hours a year zero price, and then 1,000 hours a year very high price, and then but then the average price still will stay in something like 40-50 euros per megawatt hour. And then the idea is that if wind will be 30 euros per megawatt hour or even less in future, then they don't mind that sometimes it's zero, the prices in the market. It's possible. Gregor.
You moved to Thailand recently. How are those ideas appreciated there?
Well, there's let's say that my optimism has hard time in Thailand. So they have a lot of solar resources, and they do have wind resources as well, now that we have the new turbines, that the low wind turbine technology has suddenly given them a wind resource they were not aware of, and still are not aware of all of them. So there, and a lot is happening, so a lot is built there for sure, but you also do see still investments in coal in that region, not in Thailand, but in other countries. So this, of course, is the worst possible thing also for their economy, because they will be ending up with stranded assets of coal if they still build it now. They are moving towards gas in some of these countries, and they are using the hydro better. So there are some nice things happening, but yeah, it's a big thing to get Asia towards renewables, and also something that probably will be quite critical for the climate change.
Okay. Thank you very much.
Thank you.